Yo, 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 yo. Okay, we're going to be rewriting radical expressions. So let's just get right into a lot of vocabulary, but it's all means very similar things. The biggest one is this property product of square roots. So I'll even draw a picture of all these vocabulary terms for you. So this symbol right here, this is called the radical. Everything underneath the radical, so we're going to have x's under there now. Everything underneath the radical is known as, so all of this right here, it's underneath it, is known as the radicand. So that's the difference. The radical is a symbol itself. The radicand is everything, or the number or the expression that's written under the root symbol, under the radical. And then this whole thing would just be, all of this is the radical expression. So a lot of similar terms, but there you go. Product property of square roots is if I'm multiplying two numbers underneath a radical, underneath the square root symbol, then I can separate those two terms and I'm just taking the square root of each one individually. So again, going back to this example I had up here, if I was taking the square root of 25x cubed, these are two different terms, so that's really the square root of 25 times the square root of x to the third power. And then I can simplify from there, which is what we're going to be working on today. So first what we're going to be doing is we're going to be looking at equivalent expressions for square roots, okay? And what we're going to do is we're going to do that by factoring out perfect squares. So like the square root of 63 is an irrational number. I do not know what the square root of 63 is, okay? We're not going to be plugging it into a calculator. We're going to be rewriting it. So what we're going to do is we're going to rewrite 63, but we're going to write it as a product of two different numbers. So I'm looking for factors of 63, but I want one of those factors to be a perfect square that I can take the square root out of. So I know that 63, square root of 63, is the same thing as the square root of 9 times 7. Because 9 times 7 is equivalent to 63. So I just rewrote 63 as two different products. Well, what I can do now is now I can actually take the square root of 9, because going back to that property that we talked about, I'm multiplying two different numbers here under a radical. So this is really equal to the square root of 9 times the square root of 7. And the reason why I did this is because the square root of 9, I know what the square root of, that is a perfect square. So the square root of 9 is 3. I don't know what the square root of 7 is. Square root of 7 is a prime number, and I can't take any perfect squares out of it. So my final answer is 3 times the square root of 7, and a way we write that is just 3 root 7. Because we don't have to write the multiplication symbol in between, we can attach it just like a variable. So my final answer is just 3 to the square root of 7. So this is equivalent to this. We call this like the simplified version of writing this. We're taking out perfect squares and then simplifying it. Okay, and we do use this skill when we solve equations later on, because then now I would be able to divide this by 3 and it would make it go away. So it's a way of simplifying. So the first thing is we rewrite it as factors, and we want to have a perfect square factor so we can take that perfect square out. So here we have two different examples here. Okay, so this is 3 times the square root of 27, just so you know. If it wasn't multiplication, if it was like a cube root, that 3 would be smaller and be right in here in the radical. So that 3 in front of it means it's multiplication. So for 44, what I'm looking for is I want to figure out what are factors of 44 that can add up, what are factors of 44 that but also have a perfect square in it. And that would be 11 and 4. Because square root of 4 is 2. So this is really 11 times square root of 4, which is 2 square roots times the square root of 11. Because the square root of 4 is 2, I always write that in front of the radical. So therefore I have 2 times the square root of 11 is my final answer. So this is a simplified and rewritten expression of this original square root. So you have to know your multiplication facts. Okay. So now this one right here, for this one, I have the 3 in front of it. We kind of can ignore that for right now, because this is 3 times whatever this is. And I can just worry about simplifying the square root of 27. And so the square root of 27 is the same thing, and I can keep the 3 on the outside, but that's the same thing as the square root of 9 times 3. So then that's really the square root of 9 times the square root of 3. And this is all multiplication, right? So that's now becomes 3 times the square root of 3, which is 9 times the square root of 3. So because this is 3 times the square root of 27, I'm simplifying the square root of 27 by rewriting it. I rewrote it as 9 times 3, which means I know the square root of 9. Square root of 9 is 3. So this is all multiplication. This is 3 times the square root of 9 times the square root of 3. So I simplified this by breaking it down into these two pieces. Well, that's just then once that becomes a 3, the square root of 9 is 3, so that's 3 times 3. So there we go. So these are equivalent expressions as well, but I took out the perfect squares. So now what we're going to be looking at is how we can compare different radical expressions. Okay, so what we're going to do is we want to, when I say how can we compare these two, is I want to see, are these equivalent or are these not equivalent? So I have 2 square roots of 5, and then I have the square root of 20, or 2 times the square root of 5 and I have the square root of 20. So I'm going to simplify this to say, hey, are these the same or are they different? What's going on here? So the square root of 20 is, I want to rewrite that. Well, that's 4 times 5, which is the square root of 4 times the square root of 5, which is 2 root 5. These are the same. So I can compare them by saying, hey, these are equivalent expressions. This is the same thing as this. So those are equal. So go ahead and pause, and I want you to compare both of these. And so I want you to compare these two, and tell me, are these equivalent or not? So pause it and try it, and let's see how you do. So for this one right here, I can simplify the square root of 36. Let's see here. Oh, let's see if I can simplify square root of 36. So I know my equivalent expressions are, well, square root of 36 is 6. I was about to break it down. I wasn't even thinking. I was about to break it down into square root of 9 times the square root of 4. Because 9 times 4 is 36, which is 3 times 2, which is still 6. So there's 2 ways to get there. But square root of 36 is 6. The square root of 6, I cannot break down the square root of 6 anymore. So therefore, this is 3 times the square root of 6. This is going to be an irrational number because this is not a perfect square. There are no perfect squares in this, so these are not equivalent. And I cannot make them equivalent. These two right here, well, I have 6 square root of 2. I can't break down square root of 2 anymore. Square root of 72, though, this is, let's see. There's a few ways I could write this one. But I could write it as, first thing that comes to my mind is 9 times 8. So that's the square root of 9 times the square root of 8, which is 3 times the square root of 8. But square root of 8 also has a perfect square in it as well. So this is 3 times the square root of 4 times the square root of 2, which is 3 times 2, which is 6 square root of 2. So these are equivalent. Now, another factor I could have done for 72, I could have done 36 times 2. So 72 is also 36 times 2, which then we know that is 6. So that'd be 6 root 2 as well. But this is another way to get there, is once you simplify once, make sure that there are no other perfect squares within your radical expression. Okay. So now what you're also going to do is we're going to have to rewrite equivalent expressions for radical expressions, but now we're going to have variables in there. So the process is really the exact same. Okay, is we want to find what are perfect squares here, but we want to find perfect squares for our variable as well. So here's how I would break this one down. So 63, we already know 63, but we'll break it down anyways. So I know that I can break this down as a 9 times 7, and we'll still keep this as x to the 9th power. But now I'm going to break down this x to the 9th. I know x to the 9th, let's see, this is 9 times 7, and then I know x to the 9th, I can break it down as x to the 4th times x to the 4th times x, because if I look here, x to the fourth, and x, if I add all these up, it still gets me 9. So I still have 9 x's here. Well, let me show you how we can break this down even more to show you how this is going to help us. This 9 is also 3 times 3, right? So we know that because the square root of 9 is 3 times 3, that 3 times 3 really comes to the outside. Well, because I have x to the fourth and x to the fourth, the square root of x to the fourth times x to the fourth is x to the fourth. So I can also bring that to the outside as well. Because the definition of square root is what times itself. So because I broke it down to 2 different x to the fourths, I can bring the x to the fourth on the outside. So this is gone, and now I'm left with 7 times the square root of x, which is really just, whoops, wrong button, which is really just 7x. So again, let me figure out another way to kind of help you out with this one. So what I did was, when I'm taking the square root, I'm really breaking it down to what times itself equals 9, which is 3. So, and I'm really breaking it down to what times itself equals x to the 8th. Well, x to the 4th times x to the 4th equals x to the 8th. So, but what I did is I rewrote that as x to the 4th and x to the 4th, and that's what allows me to bring it to the outside. Let's look at another one. This might help a little bit. So for 25x to the 3rd power, what I'm doing is I need to figure out, well, what can I take out of this? What are perfect squares that I can remove from this radical? Well, the square root of 25 is 5. But again, let me show you another way I can break this down. Let me just rewrite. I'm going to rewrite all of this right now. So I know I have 25 is the same thing as 5 times 5. X to the 3rd is the same thing as x times x times x. So the definition of square root is what times itself equals that. So that's why I broke it down. So I can take these pairs. I have a 5 times 5. This 5 times, because 25 is 5 times 5. That means the square root of 5 times 5 is 5. I'm bringing it to the outside because the square root of a number times itself is that number. Well, that's why I can pair it up with my x times x. X times x is really just x squared. The square root of x squared is x. I'm left with an x on the inside. So these go to the outside. This pair goes to the outside, and I'm left with the x in the middle. And I'm done. Okay. Now, really, if we look at this square root of 25 and x to the 3rd power, I can always take x squares out, because the square root, this is x squared times x, and this is the shortcut, is we know the square root of x squared, the square root cancels out the square. So this is really the square root of 25 times the square root of x squared times the square root of x. This is just another way of breaking it down. We always know that this square root symbol cancels out the x. So that's why this becomes x, this becomes 5. I don't know the square root of x, which is how we got here. So a lot of different ways to look at it. I know this can look kind of confusing, but really is what we're doing is we're breaking down this x, and if you break it down into x squares even, because we always know the square root of x squared is always equal to just x, because x times itself equals x squared. So we can always just break it down this much, then we can always separate our x's into x squares and figure out how many x squares we can take out. That'll help us out a lot. Okay. So how can you write an expression for the product of these two things without any perfect squares in the radicand? So now for this one, what I'm going to do is we're going to separate what's on the outside and what's on the inside. So I know that I have a 3 and a 2 being multiplied on the outside. This is all just multiplication. We can multiply in any order we want. So that's really just 3 times 2 times the square root of 5x times the square root of 15x to the 3rd power. Okay, so that's what I'm doing here. I am just kind of rewriting this and multiplying in a different way. So now I can kind of take this backwards if I want, though. Because if I look here, if we were able to separate, because this is all multiplication, if I was able to, so that's 6. We know 3 times 2 is 6. If I'm able to separate out multiplication into two different square roots, I can also multiply two numbers under radicals and simplify it under one radical. So I can multiply this as 5x times 15x to the third power. So now I can start breaking this down if I want to from here. So I can start simplifying this. There's a lot of ways I can simplify this. But one thing I can see right away is what I'm trying to get is I'm trying to get pairs under here, right? So there's a couple routes I could go here. I could do 5 times 15 if I want. I could go 6 to the square root. 5 times 15 is 75, and that's x to the fourth power. So I simplified this. I just did 5 times 15, x times x to the third. And then now I can then break down square root of 75 into square root of 25 times 3, which I know square root of 25 is 5. So I can bring that to the outside. And I still have the 3 on the inside. I still have this x to the fourth that I got to deal with. But that's how I can break down that 75 there. So that's one way to get from here to here. Now, I also have the x to the fourth. So this is 30 on the outside. X to the fourth is just the same thing as 3 times the square root of x squared times x squared. So, whoops, that was weird. I hate it when it does that, weird spaz. So x to the square times, well, the square root of x to the squared is x, and the square root of x squared is x. But I also have two x squares here, so really I'm just pairing those up, taking that out. So I have 30x squared times 3. Okay, so that's one way to do it, times the square root of 3, I'm sorry. And then I'm done. I can't simplify the square root of 3, so I'm all done. This is one way to do it. So what I did is, again, I just simplified these two. I put them both under the same radical because I was able to multiply these. You're able to multiply a term under a radical by another term under a radical and put it under one radical. You're allowed to do that. That's just going the opposite direction of the original property we learned. So then what I did is I just simplified this by multiplying my values, and then I just broke that one down. Another way I could have done it from here is I can break this 15 down right away. So this is 5 times x times 5 times 3 times x to the third power. Well, again, I have a pair of 5s here. So the square root of 5 times 5, well, those pairs can come out to the outside. And that's how I'm able to bring it out here, which is what I already did. Okay, I'm still left with a 3, so that gives me 30 square root of 3, and then I have x and x to the third, which is x to the fourth, which brings me right back to here. So if we look for combinations for pairs, 5 times 5 under radical means I cancel those out and I bring the 5 to the outside. So that works. Okay, so try this one on your own. Pause it, try it, let's see how we do. And then this will be the last problem of the video, I believe. Yeah, so try it out, pause it. Okay, so this is really 2 times 12x to the 9th times 18x to the 5th. Okay, so then again, what I could do is I could break down 12, I could break down 18, I can multiply these things. I think I'm going to start breaking those down right now. And I'm going to combine my x to the 9th and x to the 5th to make x to the 14th. So this is, let's see, 4 times 3. 18 is, let's see, 6 times 3. And then I have x to the 14th. So what I did, I broke down 18 to 6 times 3. I broke down 12 to 4 times 3. Well, here's a couple things I have. Now I have the square root of 4. Square root of 4 is 2. So I can take this out and bring it to the outside. I know the square root of 4 is 2. So now I have 2 times 2 on the outside. I also have a pair of 3's. So I can cancel those out and bring a 3 to the outside. So, because 3 times 3 is 9, square root of 9 is 3, so I bring that to the outside. I'm left with 6 on the inside. So I have 6, and I still have this x to the 14th here. Okay, well, x to the 14th is really just x to the 7th. So this is 2 times 2 is 4, times 3 is 12. Sorry, let's just get that out of the way. So 4 times 3 is 12. But x to the 14th is x to the 7th times x to the 7th. Well, that's a pair, so I can bring that x to the 7th to the outside. So I have 12 x to the 7th on the outside, and we're left with a 6 on the inside. I can't break down 6 anymore because it's just square root of 3 and square root of 2, and I can't do anything with that, so I am all done. And that's it. Okay, so one thing you'll notice is when you take the square root of x to the 14th, it's really just dividing it by 2 to make it x to the 7th. Okay, so that makes it a little bit easier. That's a nice little shortcut for you. But that's it, guys. So I know it's a lot of different kind of weird things and weird rules. But let's actually put for our things to remember. Let's put our things to remember. Square root of x to the 14th is just x to the 7th. That might be a nice, helpful rule for you. And then let's also put in our things to remember the square root of 3, or let's write it like this. Yeah, the square root of 3 times 3 is equal to just 3. Okay, because that shows us our pairs. All right, I hope this helped. I hope we followed along. Let me know if you have any questions. Critias out.